Now that you've seen the power of dynamic programming, let's try to apply that technique to another problem. There are countless ones to choose from. I'm going to use one known as the min-edit distance. The problem asks you, given two strings, what are the fewest number of manipulations you need to do to convert the first string to the second string? This might seem like a Victorian parlor game that C.S. Lewis might have played, but it's also very useful for bioinformatics, where you have genetic sequences and you're trying to understand the role that mutation and splicing play. When faced with this problem, there's no immediate intelligent way to solve this. I can look at two words. In this case, I've got a word great, another one create. And if I look at it carefully, I could say, well, if I convert that first G into a C, and then that's a replacement operation. If I delete that S, that's a removal operation. And if I insert another E right after the R, I will convert greats into create. And I can do that in 3 steps. Now that process took a little bit of wordplay, and you might not immediately see how you can write a program to do that without trying every possible arrangement of insertions, deletes, and removals. And this is exactly where the dynamic programming technique will work. If you can find a way to subdivide the problem up into subtasks, then you should be able to take advantage of this technique. As you know, the dynamic programming approach will use a matrix to store the results of past computations. And if I have these 3 operations, insert a character, remove a character, substitute a character, I need to find a way to relate different cells of the matrix, which were representing partial solutions, to the newer solutions that are being encoded. Here, when we're done with our small example, is the final matrix that will be generated by the code. It demonstrates in individual cells the cost it takes to convert a string from one to the other. You can see some of these numbers that come to mind. If I have greats, which has 6 letters, if I want to convert that down into the empty string, it's going to take 6 deletions. Moving vertically means you're removing a character. If I want to move to the right, that means that I'm adding a character. So to take the empty string and convert it into create will take 1, 2, 3, 4, 5, 6 steps. The real trick is to understand how to deal with replace. And what replace will do is, given 2 strings, it will determine are they the same length, and what is the character in the very last spot? Was it the same in both strings? And if so, there was no replacement necessary. In the matrix, when you look at the replace operator, that'll be a relationship between a diagonal cell to the one to its lower right. All of this will be made visible in the code, but again, when you look at dynamic programming code, it looks surprisingly brief, and the real logic is trying to capture the ability to determine the next solution based upon the composition of earlier solutions that were computed. Let's now implement min-edit distance in Python. As you might expect, as a dynamic programming solution, we're going to need to have some matrix values to store the results of past computations. We're also going to need to have some nested for loops to iterate over past solutions and generate new solutions. Let's start with that last point. When it comes time to determine whether you can take a string and convert it to the other string by insertions, removals, and substitutions, I need to frame that problem as a minimization problem. The way we do that in dynamic programming is to say the cost of determining whether string 1 up to position I can be converted into string 2 up to position j is based on the replacement cost, or the removal cost, or the add cost using earlier solutions. These 3 costs are represented here. The remove cost says, well, imagine that you had a string that was 1 character greater, then you remove 1, and then you add a cost for that operation. The add cost says, what if you had a string that was 1 character smaller, and then you add 1 to that? That gives you this cost here. The final cost is, what's the replacement cost? And that is based on whether the particular string at that index location, index I for one string, index j for the other, is the same. And so I have a cost where I assume that they're different, but if it turns out that they are indeed the same, then I say there's no cost in substitution because the character is the same. Based on these 3 subtasks, I can now compute the minimum value of those three, and that is the one I use in the dynamic programming minimization. For this to work, I need to set my problem up, and that's where the min matrix is set up initially. M records the minimum cost known to date. It starts out being a rectangular matrix because the two strings could have different lengths. And I need to populate the values with some reasonable ones. So initially they're all 0, but then the characters in the topmost row, those are going to be incrementally based on the length of that string, representing that string number 1. And then the matrix elements on the vertical side of this rectangular matrix will be representing the cost for string 2. So I have a rectangular matrix. Initially they're all 0, and then I have the topmost row be 0 through n, where those are the number of characters in string number 1, and then 0 to n on the left-hand side, those are characters for string number 2. And then through this double-nested for loop, I let the magic of dynamic programming do its work, constantly computing problems of ever-increasing size. Recall how dynamic programming solves problems with the most constrained form and then slowly relaxes those. The most constrained form is when I don't even allow substitution and all I allow is addition. And then I slowly add on these different capabilities using this nested for loop to try each one in turn until I get to my final cost. I'm going to print the value of the matrix just so you can see the total computations, when in fact all I really wanted was the minimum edit distance. So I'm going to use the example that I had before, from greats to create. The final answer is 3. There are only 3 operations that are necessary. But as you can see, it computes every possible sub-problem so that it's able to compute the overall problem as needed. We can do some simple tests as well. There's no need to have any operations when you're given the exact same string. And finally, if you have a string and you want to convert it to the empty string, I just have to delete all the characters. And presumably, if I had the empty string and wanted to convert it to an actual string, I'd have to add the characters. So this particular function contains all the elements of dynamic programming. It uses a matrix to store the computations that are needed for the task at hand. It uses a nested for loop to incrementally relax the constraints, starting with the most constrained form and then slowly adding on more capabilities. And in each step, it computes using a minimization function. Which of the costs is the minimum one? I could change this if I wanted to keep track of a pred link that would allow me to record each of the individual operations. But I leave that to you as a small exercise. This completes the implementation of min edit distance.